Okay. Connection okay. Connection okay. Okay. So before the file, I just want to remind you again of no Wi-Fi, no video taping, no photos, just the file. Okay. So second round, opponent challenge the reporter.
We would like to challenge problem number 16, quotient calculus.
Problem 16.
Okay, so we would like to accept the challenge.
Okay, challenge accept. Problem number 16. Please write down your representative's name on the blackboard. The reporter, you have 5 minutes to prepare, so you can start anytime. reporter, you can take a floor.
My name is Ryan, and I'm from Team Trouble. So the problem I will be reporting today is problem 16, cushion catapult. Here's the problem statement. It states that if you place an object on a large air cushion and drop several other objects in such a way that the first object is catapulted away, we have to investigate how the exit velocity depends on relevant parameters. So our main focuses for this problem is how the relevant parameters affect the exit velocity and what are the conditions under which the exit velocity reaches its maximum. So here's our overview of my report. First, I'll take a look at phenomenal observation, and so our theoretical approach to the problem, the methodology of our experiment, the experiment itself, data analysis, and lastly, conclusion. So let's take a look at the phenomenal. So take a look at this part right here. Right here. This is the object right here. Okay, this is a model simulation of the process of the experiment. So our theoretical approach to this problem. So in our initial preliminary experiments, we discovered that if we increase the release height, the exit velocity also increases. So let's take a look at this video. Notice this height right here, and the object is right here. Okay, we increase the height on this one. The ball is right here, and the object is here. So we also, in our preliminary experiments, we also discovered that if by changing the mass ratio of the two objects, M1 is the ball, and M2 is this one. So by changing the mass ratio, it also resulted in different initial velocities. So you can note that the video on top is the one with the lighter mass, and the video on the bottom is the one with the larger mass. So to prove this, how do we prove this? We use the work energy principle. So considering that no energy loss is involved in this experiment, so 100% of the energy used is transferred. So by using M1 H1 equals to M2 H2, we could get that the H2 equals to M1 times H1 over M2. And so how we calculated the initial velocity is by using a square root of 2 times G times H2. So we can see that the mass ratio M1 over M2 and height H1 both affects the initial velocity. We also discovered that by changing the distance between the two objects, the contact point of M1 and the original position of M2, it also affects the initial velocity. So let's take a look at our video. So this one is where the contact point is very close. This is the M2. This is the contact point of M1. So it barely catapults away. And this is when it's, I think it's 20 centimeters apart. So what our theory on this is that when the kinetic energy of M1 is dropped to a cushion, the energy transfer in the cushion is traveled by compression wave. And so if the distance between the contact point and M2 is too close, the wave might be too dispersed. If it's too far, the wave may have dissipated too much energy due to friction. We also discuss about elasticity. So by changing the elasticity of a cushion results in a change of the coefficient of restitution, which leads to a difference in the energy transfer efficiency. So our methodology of the experiments. So this is our setup. So we used a pulley system to release a ball, and M1 is ball, M2 is the objects, and we used an air cushion here. So how measurements were taken. So you'll notice in the background there that there are black lines and red lines. So we first defined this unit in tracker, and so black lines are 5 centimeters apart, whereas black and red lines are 2.5 centimeters apart. How we measured H2 is we marked the initial position right here, and the maximum height reached, and by applying that, we used square root of 2gh. So this is a part I have to separate talk about, is that when we changed the elasticity of the cushion, we used different heights of the cushion. So it was easier for us to measure So by changing this, we're also changing the volume of the cushion and also the pressure inside the cushion. So our variables of this experiment. So the independent variables are listed here. So in our experiment, we discussed release height. Experiment 2, we discussed mass ratio. Experiment 3 is our distance between the two objects. Experiment 4 is our cushion height. And these are our control. So this is a diagram of parameters. So what we're changing in experiment 1 is right here. Experiment 2 is the mass ratio between M1 and M2. Experiment 3 is the distance of the contact point at M2. And experiment 4 is the height of the air cushion. So how energy loss was calculated. So this is what we'll use in our data further in my report. So original potential energy of M1 is equal to M1 times G times H1. Kinetic energy of M2 is calculated half of M2 times V2 squared. So the energy is calculated by using potential energy to minus the kinetic energy over the original potential energy. So this is our data for experiment 1. So you see that results in a pretty linear graph with a R squared of 0.99. Our blue dots are modeled, considering that if energy is transferred 100%. So the correlation between release height and energy loss is shown. So you'll see that in our graph that as we increase the release height, the energy loss is lower. The mass ratio of two objects is experiment 2. So let's take a graph here. So in this graph, you'll see that if we increase the mass ratio, the initial velocity also increases, which matches up with our theory. And the correlation between mass ratio and energy loss is right here. Experiment 3 is we discuss the distance between the two objects. So what's special about this graph is that you will notice a optimal distance where it reaches its maximum velocity right here. So it starts out at 5 when it's 5, and then increases and reaches its peak at 20 centimeters, and then starts to fall out onwards. So the correlation between the distance of two objects and energy loss. So you notice the dip right here. So when the energy efficiency was the highest of all these experiments. For experiment 4, we discussed the amount of air in the cushion. So this is our results. And you notice that it also appears to be a curve, reaching its optimal cushion height of 8 centimeters. This is energy loss and amount of air in the cushion. And our analysis of our data. So for experiment 1, after we plotted our dots, we marked the trend line, which R squared equals 0.99. And what we got is that for every centimeter we increase in the release height, the exit velocity increases by 0.19 meters per second. In our experiment 2, our data also suggests a linear line. So what this indicates is that a higher mass ratio, the higher the exit velocity. For experiment 3, it just shows a bell curve right here, and so optimal range is around 20 centimeters. For experiment 4, at a height of 8 centimeters, the cushion height, it resulted in the lowest energy loss. So our conclusions. So the maximum velocity reached at 40 centimeters with a setup distance of 20 centimeters is 4.164 meters per second. And the optimal setup still has an energy loss of around 93.5%. And so you'll notice in our graph that our energy loss is way above 90%, even if it reaches its optimal. So what we think is involved in this is that we didn't consider air resistance. So I said our initial velocity is calculated using square root of 2gh. So this h, will, air resistance will have an impact on h2. Also, as I said, the energy is transferred using compression wave. So inside the cushion, while the compression wave is traveling, it experiences internal friction. So this is where energy is lost. And also, M1 energy didn't fully transfer to the cushion. So after M1 drops, after M1 is dropped onto the table, the velocity is at 0, indicating that the cushion didn't fully receive all the energy from M1. So after we plotted our data, we used normalized our data set, so ranging from 0 to 1 from all of our data sets. And this is what we discovered. So after we can see that for release height, the range is 0.898, indicating that this is the main parameter affecting the exit velocity. And the distance between objects and the cushion height is around 0.646 and 0.658. And what affected the least in our experiment is the mass ratio. Thanks.
Okay, that's a question from the opponent.
Okay, thank you for the first from the reporter. First, I'd like to know, do you control the air amount in the cushion?
Air amount, yes, we controlled it in the cushion height.
Now, how do you control the surface of the cushion?
Surface of the cushion. So in our methodology, right? Wait, so you see that we placed a plastic board right here. So after each experiment, we just placed it here. So it's flat.
What I mean is, will the surface turn back to its original shape?
After experiment.
After this?
Oh, so after M1 is dropped.
Yes.
The shape deforms.
Okay. Do you control the shooting angle?
Shooting angle, yes, it's all 90 degrees onto the cushion.
I mean the second object, which will be bumped up. The object.
Bumped up.
Yes.
No, we didn't.
Okay. What will the
Could I change my answer? So only in our distance. So when the variables was the distance. Otherwise, it was all 90 degrees. So we found a optimal spot that would launch at 90 degrees. So we could use it in our formula.
Okay. What will the work energy? Because you mentioned that there will be energy loss.
Yes.
What will the energy transform to?
Oh, so when M1 is dropped, you could actually after M1 is dropped right here, there's still speed on M1, right? So so that means that energy has to transfer.
So you think it will be kinetic energy?
Lost in forms.
Kinetic.
Yes, M1 and
Okay.
when it's traveling compression.
So do you consider the contact area between the cushion and the floor, the table?
This spot.
Yes.
No, this is constant. So we use the same size of bag in our experiments.
Okay. I think it.
Okay. So, opponent, you have a 3 minutes.
Okay. spiritualist and fellows competitors. I'm an opponent from team our borrowers. And today I'm going to oppose problem number 16, quotient particles. And this is a problem statement. Place an object on a large area quotient and drop several other objects in such a way that the first object is catapulted away. Investigate how the velocity depends on relevant parameters. And the main focus will be how the relevant parameters affect the exit velocity, and what are the conditions under which the exit velocity reaches the maximum. And this is the brief summary of the order. For the observation and theory, they use the work energy principle to explain the experiment. And also, they mention that quotient is compressed, the energy is transformed to a compression wave. And also, they talk about elasticity. And for experiment method, they use Foley system to release the ball. And they also use tracker to analyze the experimental result. And they calculate the energy loss. And for the data analyzed, they analyze the height of the drop and the initial speed is, they think that the height of the drop and the initial speed is in a linear relation. And also, the higher the more energy, there will be more energy loss. And for conclusion, they found out that height of A is will have the lowest energy loss, and the maximum velocity reaches at 40 centimeters. And air resistance, internal friction in the quotient may cause low of the energy loss. And these are the pros and cons of the reporter. For the pros, they have a clear demonstration of the phenomenon, and they organize results in data, and they also consider various variables. For the cons, they didn't find a specific correlation between factors, and they can try to connect theory and the experimental result, and they don't have the error bars, and also the time management is quite full. And so in the discussion, this will be the discussion part I would like to read with the reporter. First, for the theory, I would like to ask, what will the mechanical energy transform? Since the reporter mentioned that there will still be velocity of the first object they release, but I think the energy will transform to other kinds of form. And for the experiment method, they didn't mention that how to control the loss of the ball and location, because it seems that the ball is still swinging when they release the ball, which may cause some deviation. And second, how to control the surface is the surface of the quotient. And third, to control the air amounts. Since that in the experiments they use a zipper bag to do the experiment, so I think there may be some air decay if they use a zipper bag. And also, the zipper bag won't turn back to its original shape when they finish the experiment. So I think that there may be some better choice of the material. So for the data, they don't have an error bar, and whether the relation is linear, they didn't mention this. And for extension, I would like to know that the contact area of the mass and the quotient. So this will be the discussion with the reporter, so I would like to invite the reporter for the discussion.
Start the discussion.
Okay. First, I would like to know, since you said that you have controlled the air amounts, but I think the zipper bag will have some air decay. What do you think?
Oh, so we measured it after each experiment. So if there is some air losing, the amount won't be significant.
So do you think it should be controlled?
Yeah, we controlled it.
But I think that the air will lose from this zipper bag, because the exit is not well fit.
Oh, yeah, it's probably a factor in my, so you'll see that energy loss. That might probably be my experiment error, but I think it won't be that too much significant.
Okay, so do you have an actual number of the air amounts in your quotient?
No, we didn't. Because we used type rate.
I suggest that maybe you can put a tape on the exit of the zipper bag to make the air coming out to be less. Let's move to the wood. What I have mentioned is that, for example, this is the quotient, and this is the second object that you bounce out. I think that if this is bounced out, will the shape of the surface of the cushion turn back to its original surface.
Okay, so this is the original, right? So I
Yes.
want to draw this. Next, after it's impacts, it starts deforming, right? So it starts to change shape on the surface too. So after that, N2 is launched, right? So N2 is break. And then shape so I kind of want to discuss like the energy loss. So after M2 is launched, because energy is transferred using compression rate, right? So there's a delay. So after this amount of cushion changes the shape, it starts making M2 starts to fly, right? So after M2 starts to fly, if the transfer of the compression wave is too slow, a lot of energy is
But
lost.
what I mean is that since you place the object here, so it may have like be lower, right?
Yes.
But if the object is far away, will it turn back to its original shape?
It will turn into this. So after it's compressed, this part is where it's low, so this is the ball, and then it will have kind of this shape. Do you want to look at the view? So you see that?
Oh, okay. But I suggest that you can use a material which can turn back to its original shape, like some balloons or other metal. Because in this situation, you are difficult to know what is the change of its height, right?
Yes.
So I think that maybe other kinds of material will be better for you, like the material which
But
can.
what's the goal with like changing the material? So
Because
what's that?
it will have the elastic energy.
Yes, yeah.
And so you know the change of the.
But it would still be important to this. So if you change the elasticity of this, it would be a force here, but it would just like go back to its original place, right? So there's still energy loss right here. It's
Okay.
just whether it shows or not.
Okay, thank you. Let's move on to the next section. Let's talk about the energy. You said that there will be an energy loss, which is because the first object still has the velocity, right?
Yes.
But I think the energy was.
But I'll kind of like this throw through, but yeah. So what I mean by velocity is, so you'll notice that this and this didn't change quite.
Okay, I know what you mean.
Okay.
But what I mean is that I think the energy will still transform into heat. Do you agree?
Yes, I agree. So energy are lost in heat, and so M1 is right here, and also the energy to light. So it will cause this.
So what is the heat come from? Heat.
Yeah, collision.
Okay. I want to clarify to you is that it's because of the friction between the torsion and the.
I think it's a combined factor of all these.
Okay. So I think that the energy loss may transform into the heat.
Yes.
Even though what you mentioned that it will still have velocity is quite true, but I think it will mostly transform into the heat. What do you think?
Yeah, I think that energy loss is heat. Yeah. I partly agree.
Okay. So do you want to explain more?
Explain more. Oh, they also changed the volume and the pressure of the cushion, right?
Okay.
So that's probably.
Okay. Let's move on to the next section. Let's talk about the contact area between your cushion and your floor.
Yes.
So you said
Yeah. We concluded.
But if your object is released, will it change its contact area?
So we actually taped it. So the cushion looks more. Like this.
How about here? Will it be contact more?
Oh yeah. So while it's dropping, this point might touch the ground.
So do you think it will affect or?
I kind of don't understand. So what do you think that this contact area is about?
Because if there is a force that go that in this direction, there will be a force that go.
Yes. Yeah.
So I think it will affect.
Oh, yeah, understood. So, yeah, I think
The
that's.
counter force.
Yeah, okay. So, yeah, I think that's my, but I think that it won't be significant, because So in our data, M1 is like 30 times it. So I don't think this works. Okay.
But in your experiment, it seems that the object will bounce the floor.
Bounce.
Touch or
Yes. Yeah.
Do you think that it should still be on the torsion?
Oh, I think that we could optimize like if we increase the distance or the amount of air motion to let M1 be like when it stops, when the velocity is 0, M1 is 0. So I think that we can control the I am.
So I suggest that maybe you can make your torsion become bigger.
Yes.
So that don't let the object you release to touch your ground.
Yes, but this also changes elasticity, right?
Yeah.
Yeah. So yeah, that's a factor that we consider, and the results were that this is the height of the track. And our results were like, if you pumped it up to that, it was around like 12 centimeters. And what we got was like the kind of this. So if we use that,
but in this situation, did you consider the bound between the object and the ball? I think this is the ideal.
Oh yeah. I kind of understand what you're going on, but
So what I mean is you need to avoid this kind of situation.
So what do you recommend? Do you have?
To be that the become bigger.
Yeah, but could you like? Is there any possible way to achieve this without like changing the system?
I think maybe the height should be like bigger from this. For example, like go to 15.
Oh, so just like use a very large volume of air cushion.
Yeah. Okay. Let's move on to the next session. I talk about the location of the ball. You said you change the distance between each
Yes.
balls, right?
Yes.
But how about the place? Its location on the torsion.
Its location on the cushion. So actually, you plot the dots. So this would be a contact point,
Yeah.
and then you plot like 2.5, 5, 7.5. This is the place of the
Okay. But
the pulley system is right.
okay, thank you. But this is the surface of the torsion. It seems like it's a curved surface, so that your shooting angle will not be controlled.
Yes, so I would like to clarify on how I calculated the initial velocity. So
Okay.
we calculated the initial velocity using the tracker. So it didn't matter if our launch angle are different, right? But what we used stereo QGH is for our model, and when we controlled it for it to be 90 degrees.
Yes. But since that you have got the height, right?
Height of what?
Height of the object that is from up.
Oh, you say
Height.
maximum height.
Yeah. But if different angle, it will not be controlled.
Yes, but we didn't. So which graph were you?
Which have the
Height. No, the height is height of M1.
oh.
M1. This is H1.
Okay. Do you control the location that you release the?
Yes. So that's why we use a pulley system. So we could.
But in your demonstration video, it seems that the ball is still swinging.
Oh yeah, but that's for observation. Yeah, that's.
So I suggest that maybe you can wait for the ball to like stop and then to release the ball. But I agree that the pulley system is a good tool that you can use it to.
Yes.
Okay. I think this is. Okay. I think this is thank you.
Okay, so the question from the reviewer, the opponent summarized.
Okay, we separate the discussion into a few parts. First, we talk about the air amounts in the torsion. They say that they control the air amounts, but I think that there will be air decay in the situation. So I think that they should change another material. The second, we talk about the energy. They mentioned that there will be there will be still some velocity of the object they release, but I think the energy will also transform into the heat because of the friction between the balls and the cushion. And also, we discussed about the contact area between the cushion and the floor. I think it should be considered because that if the first object is released, there will still be the counter force that will go up and affects the experiment. And also, we talk about the location of its object because that in different locations of the cushion, it might be different shooting angle.
Okay,
So I think
time's up. Okay, so now the question from the reviewer to both reporter and opponent.
Thank you for being to the reporter and opponent for the discussion. And first question I want to ask the reporter: do you consider any rotational kinetic energy of the object as much in your model of conservation of energy?
Oh, no, we didn't consider.
And
I think that it should be considered.
And in your experiment, did you consider any? Because you said that the bag, there's no air peaking, and the bag goes down, but the object is compacted, right?
Yes.
Did you consider any motion of the object that's getting dropped going back, rebounding up?
Could you clarify?
Like when you drop an object and you have, you said you have elasticity, right?
Yeah.
So wouldn't that also shouldn't you consider the rebound of the object going?
Oh, but it just dropped onto it. So if the mass is light enough, it might bounce, but our mass is like way larger.
Do you consider any different inflation of the cushion, stretching at like 80% like volume or like 100%?
We defined that using the cushion height. So we didn't want to measure the volume, so we used the volume height.
So do you know about the cushion acting as a rigid object when it's fully
I think it's pretty smooth.
No, what I mean by rigidity is that there will be no airflow due to any airflow since it's completely inflated.
Yes.
Do you agree?
Yes. So in our experience, so you'll notice that after we increase the cushion height by a lot, the initial velocity didn't actually increase, but rather decreased.
So do you agree to the point that of the rigidity of the object? And do you think that opponent should, like the reporter should have considered that part?
yes, I read the surface of the cushion.
Okay, thank you. So for the reporter, in your experience, were there any sounding during your experience?
When it bounced, when M1 is touched, contact.
Do you acknowledge that sound is an important factor of loss of energy?
Yes.
Do you agree that
Yeah.
sound is a factor?
Yes, I agree, but I think that the heat between the heat is the main factor of the energy loss.
So you're saying that the heat is the most important factor of energy loss in his model of conservation of energy, correct?
Yeah.
Okay. And for the reporter, does your cushion rotate? Like if the drop object hits the cushion, does the other part go up?
Yes.
It does, right?
It goes up, but we actually stabilized some points.
No, I mean the end.
Oh yeah,
edge part.
change.
So
Yeah.
do you consider any torque of the cushion itself?
It might act like a torque, but we couldn't actually pinpoint it.
So you didn't consider in your formula or like theory, correct?
But we couldn't actually use leverage to use.
Just answer different.
No.
Do you think he should have considered torque of the system?
Yes,
Cushion.
yes, but they also still control the area between the cushion and the door. So I think that it is controlled.
Okay. So the time for reviewer to prepare your report.
是每个人都有上的。声音是每个人区别在一起。
sure, you may take the floor.
Okay. Hello everyone, my name is Lim, and I'll be presenting all measures for cushion catapult. And this is a problem statement: place an object on a large air cushion and drop several other objects in such a way that the first object is catapulted away. Investigate the electric velocity depending on the relevant parameters. And the main focus of the reporter was how did the relevant parameter affect the exit velocity and in what conditions the exit velocity reaches maximum. And this is a reported performance. First, for the phenomenon, he talked about when release height increases, the velocity also increases, and drop a metal ball and launch into the washer. And for theory, he has work energy principle and conversion wave, and experiment he has distance between the two objects, and he also has height of the object for the volume. And the pros for the reported was the good display of experimental setup, multiple theory for different aspects, and he listed the parameters out, and he had a video, and he shows his tracking method. The cons, he had no consideration of the torque of the bag, no consideration of surface area, theory is not linked together, no error bars, no explanation on pressure, no consideration on angles, and no consideration on angular acceleration in his model of conservation of energy, lack of theory to experimental result analysis, and no consideration in volume of the cushion, and his experimental setup fails to control the swing during the drop. And also, he doesn't explain why the relationship between the data is linear. For the opponent, he summarizes the theory, experimental method, data analysis, and conclusions. And he brings up various methods to correct errors in the experiment. For the pros, he mentions solutions to solve various errors such as loss of air or surface contact, also with the mention of heat. And the con, he only discussed the part of the experiments, and he didn't really comment on the theories they had. And this were the discussions. First, the top opponent questioned the reporter that how to control the amount of air inside in the experiment. And zipper bag, loss of air, and they suggested taping the bag. And reporters said they control the air, but the energy loss of air is a part of the experimental method. We agree with the reporter that the error from loss is minimal. However, we agree with the opponent that the reporter should have to seal with tape. And the next part is, what will the mechanical energy be transformed to? And the opponent mentioned heat as a major loss factor. The reporter says it transferred into compression weight, and heat is also a factor. But for us, we partially agree with the reporter. We think that kinetic energy, sound, movement of cushion, and work in the cushion is more important than heat. And the next one is, how can we control root of law? And reporter said we can do for only the object, and we think the pulley system will be good to use, but the swinging will affect the results. And next, the data analysis doesn't explain why there is linear relationship. The reporter didn't mention anything about that, and what we think is that the range of data was too small, and it should be increased, and eventually it wouldn't last in a linear relationship. And the point finishes the torque acting on the cushion, overall energy transfer in the phenomena in their discussion of conservation of energy and inflation of the bag, which causes the rigidity of the cushion, different sizes of the bag, different phases, like impact, dropping, launching, and the restoring constant K for the plastic bag, dissipation of energy in the system, ideal gas law, properties and of air in the cushion, angular velocity and angular acceleration of the object, and also with the cushion, and the material properties, the motion of the yeah. Thank you.
All right. So, conclusion remark from the reporter.
This concluding remarks are of problem 16, cushion catapults. So in my summary, I used work energy principle and compression wave to describe the energy transfer. I also used a lot of different parameters that affect the exit velocity and energy loss. And we also discussed about multiple possibilities that might affect the energy transfer efficiency. And after normalization, we got that the release height affects exit velocity the most. Opponent's summary is that they discussed conditions that allow for the best exit velocity and where energy would be transferred after impact. And in our experience setup, air decay might occur. So what we discussed is that the details of energy transfer processing, including the energy loss caused by heat reduction and friction's influence. There are some areas for improvement of my experiment setup, and whether the contact area will affect the results. The surface of the cushion causes a shooting angle will also be different. So concerns for resolve is that we should use different methods to improve my experiment setup and to change the material type of my cushion. We should also consider several other parameters that would affect the final exit velocity. Thanks for listening.
Okay, good. So now it's a question from the jury.
When the projected object is maximum,
Yes.
does the end of the object has kinetic energy? This kind of the reviewer.
So are you talking about when after the collision with the launch object?
Yes, the object already has the maximum height. Does the object at that time has kinetic energy or potential energy?
Well, if the potential energy that was initially from the dropped object will be fully transferred as the potential energy of the object that's getting launched. So there will be only potential energy without any kinetic energy affecting the launch object.
I think if the object is at the topmost place, that its velocity should be zero, so I think that it will only be potential energy in this situation.
I think it should be discussed in two parts. So whether the launch angle is at an angle or is it 90 degrees. So if it's 90 degrees when it reaches its highest point, the exit velocity is indeed zero. So the kinetic energy of that point will be zero. But when it's at an angle, it still has a initial velocity in the x-axis direction. So that's when the kinetic energy won't be zero.
All right, so
I got a question for the reporter. In your experiment 3, you said the maximum something occur at distance of 20 something?
Yes.
What if you change the volume of the cushion?
Yes, I
It's
think.
going to change?
Yeah, because I think that the point where it reaches its maximum velocity is where a compression wave is amplified. So I think that because the geometry of this cushion is kind of weird, in a way that I think by changing the volume of the cushion, the optimal distance will be different. Because
The maximum distance will be changed? Or?
what do you mean by that?
I mean, because you have the maximum occur of 20 centimeters or something away, right?
10 centimeters means that
I mean, the
initial
distance between.
yeah, and 10 centimeters is where the initial velocity is the highest.
So my question was, what if you change the volume of the cushion? Will this change?
I don't think so. Wait. Yeah, I think that will change because the geometry changes.
In what way? Let's say you increase the volume, and so this number is going to be what?
I think it will be low because where the compression wave is focused, it would be at a closer.
Higher volume.
Yes.
question? So, maybe I think the reviewer probably point out that the air in the back may be want to consider a little bit more. Do you have more comments on this?
Yeah. So if you think about the surface area of the object, if you think about the surface area of the object, the surface area is correlated with the pressure that will be applied to the back. So, and since the pressure is equal to the force over area, if the same amount of force is applied to the cushion, it will be because the pressure that will be applied to the back will be lower, and then the change in pressure that will be calculated will also be lower, and that will eventually cause the discrepancy in the results of the experiments and the airflow in the calculation of the airflow of the back, which will cause the exit velocity to actually change. Exit velocity to change from what is reported.
think that if the cushion is like too full, with too much air inside, that the air translate inside will be more difficult. So I think that they should have a, it's too stiff, that the air translate in the cushion will be more difficult. So I think there should be a capable amount of air inside. It shouldn't be like too big, the amount too much.
I agree with the opponent. So when the volume inside the cushion is too much, it's hard for the compression wave to travel. So that might cause the energy velocity to be lower.
All right. No more further question. Let's make a grading. Let's show the score. First for the reporter. 4, 7, 6, 6, 6. Then it's for the opponent. 7, 6, 6, 7, 6. Then it's for the reviewer. 8, 5, 8, 6, 6. So anyone want to comment on your score? I may comment on my score on the reporter. I give a score 4. Below 5 is because I think the average 5 is do the average job, but I think the reporter you have the experiment, but you need to be making more subtle, more well controlled in several ways. As pointed out by the opponent, also the reviewer. Of course, the data analysis is a bit. You don't have to be thorough control. You didn't repeat the experiment maybe enough time, and so that make a little bit poorly presented for your experiment. So that's why I didn't give a very high score. So if no more further comments, let's conclude this round. Thanks for everyone.